Hi everyone, welcome back. So this time we're going to do a little bit more involved example. So let's say that you have a rod, and that rod is making up the bridge we've been talking about earlier. And you know that 10,000 newtons of force is going to be applied to that rod. And you want to make 99.99% certain that this rod will not fail. Well, what do? Well, for a rod, the way you know it's going to fail is if the stress that it exhibits or it endures is greater than its max tensile stress. This is a steel rod, so it can't take more than 290 megapascals. Megapascal is a unit of pressure or unit of stress. So how do we calculate stress? Well, I gave it to you here. It's force over area. Now you know what that force is. It's 10,000 newtons. Now what is the area? Well, I tell you in this problem statement that it's a circular steel rod, and you have to figure out the diameter. Okay, so circle, I can figure out the area of a circle. So force, 10,000, area of a circle. So that's all good, but where is my big set of data here? I don't have it. So how do I know what the standard deviation of my area is going to be? If you don't have a bunch of data, then what you typically do is you do the square root of your average value to figure out the standard deviation. Now, if you're wondering, like, well, how would the area of my rod change? Like, they're not going to make something wrong. What you don't realize is that somewhere inside of your rod, there's likely a weak point. And so the effective area of your rod is actually probably much smaller than you realize. There can be cavities inside that rod. There can be cracks. There can be cuts in the side, notches that are all effectively reducing its area. So even though, yes, you're right, that a rod would normally be made to 1/2 inch, and the whole length of it would be 1/2 inch. Inside of it, it might not be completely solid, and that's where our standard deviation in area would come from. Okay, now from the problem statement, we can calculate what this 99.99% limit is going to be. This is the smallest area possible because area is in the bottom. The bigger the area is, the less our stress will be. That makes sense. The more wide your column, the easier you can take things. So we're going to figure out what the smallest it could possibly be is. So we can figure out what our average value should be to avoid that. Okay, so we have force over area. If we look at this, what we realize is we can calculate the area from the force and the stress. So area is equal to force over stress. So that would be equal to 10,000 divided by 290. So 34.5. That is the smallest, absolute smallest area that we can have and have it work. Okay, that works. So let's calculate it. What's the diameter? You don't know how to do. I think it's obvious. It's a number. Okay, hopefully you're getting extremely worried about this point because you're like, I have no idea what to do here. There's a whole lot of algebra. You can't actually solve it algebraically. There is a way to do that. I'm not meaning for you to do that right here. It's very difficult. So let's walk through it together. Let's just guess. That's what I tell you to do, so we're going to do that. Let's guess. I'm going to say 4. Okay, now I'm wrong, apparently. You can actually cheat if you wanted to and figure out the right answer, but don't do that. Now, what's the area of a rod that's got a diameter of 4 millimeters? Well, it's equal to pi, which is a function in Excel to get the exact value of pi, divided by 4 times our diameter squared. So right here, and squared. And I didn't actually... Oh, I did click it, but it did not actually give me the, there we go. Now this is saying good. It's not saying this is the right area because it's not. It is just saying that is technically the area of this circle. Okay, standard deviation. We don't know what the standard deviation of the area of our object is, so we're just going to take the square root of this. So equals, square root is another one of those wonderful built-in functions. And I plug it in. And once again, it's saying good only because this is actually the standard deviation we should have calculated. The equation's right, not the number. Okay, now what's the area of the 99.9% limit? Well, it's 34.5. Yes, but based on what you've calculated, what is the area of the 99.99% limit? Now here's where it gets a little bit tricky. Remember that the way these normal distributions work is that the values get bigger as we go to the right. So you're thinking 99.99% is up here. But it's wrong. That is the biggest area. We don't care about that actually. The bigger the area, it won't fail. We care about the smallest area. This is still 99.99% above that value, which is what we want. We don't want any areas smaller than this. And so if we're typing it into our norm.inverse function, since it's on the left, not the right, it would just be 0.1% or 0.01% for this problem. You got to remember that. That's an important detail. Otherwise, you'll be calculating a much too small area to calculate. Because remember, whatever our average area is, it should be bigger than this. It has to be bigger than this or it will fail. So, we're going to use our equals norm.inverse function. Probability would be 0.01% because we want the left side, not the right. And then I'm going to click my average area, which is just what I've calculated so far, and the standard deviation. Okay. And it's negative 0.6. Does that seem like a good idea to you? For one, you can't have a negative area. That just doesn't work. Making sure I did everything correct here. Yeah, that just doesn't work. So obviously this is wrong. Okay, now solve it. Where's the algebra here? Can you figure out the algebra? Probably not. And that's okay. I'm not expecting you to, because luckily for you, Excel has an amazing thing called goal seek. Now I have a bunch of different steps about how to use goal seek. It will show you exactly how to do it down here. And this is great for solving algebraic equations. You can only solve functions of one variable at a time, but you can still solve them. Now, luckily for us, this problem is a function of one variable. This diameter changes the area, which changes the standard deviation, which changes this value. And if we can find the diameter that will change this to 34.5, we found it. That's it. That's the diameter of our rod. That's what it needs to be, the average diameter. Okay. So how do you use this magical goal seek function? Well, first you select what you want to change. And then you go up here to the Data tab. You find the What If Analysis drop-down box in the Forecast section. And then there's Goal Seek. When you click it, it's going to open up a little pop-up box. And it says, Set Cell, this is the one that you hope will change to what you want it to be. You're not trying to change this value directly. You want to change your variable, and then this guy will function, will be a function of that. And so I want to set this cell to a value of 34.5. I have to type it in. I can't use the cell reference. By changing this cell, I want to change the diameter so that my area at that 99.99% limit will be 34.5. Okay. So if I do that, I click OK. It runs, and boom, it's done. If I like the number it gives, I click OK. And you finished. Goal Seek is magic. Use it in all your problems. It can solve them for you, and if you don't like the answer, just hit cancel and it will set it back to what it was beginning with. So this tells me that I need an area of 64.33 on average to make sure that with variation, there's only a 0.01%. I'm a 99.99% certain that it will not fail. Okay? That's how I have to do this. So you see there's a little bit more calculation here than you might expect. But it's still good stuff, and it's still extremely helpful. I hope that you'll really try to dig into this and learn it well, because Goal Seek is amazing. Well, I hope this helped you, and I'll see all of you next time. Bye-bye.